I'm going to be talking about logarithms, logarithms to the base 10. So for example, if I have a number which is 100, I can think of that as 10 squared, or 10 to the power 2. So 2 is the logarithm of this number, 100, to the base 10. 1,000 is 10 to the 3. This is the logarithm, the 3, and it corresponds to the number of zeros there. It is logarithm of 1,000 equals 3. I can do 10 to another number. So for example, 10 to the 1.6232 turns out to be 42. That means that if I were to take 10, that means that the log to the base 10 of 42 is 1.6232 to 4 significant figures. The reason it's useful is multiplication. If I have two numbers and I want to multiply them together, it's easy to make mistakes because there are a lot of little operations that have to be added up. If you go through logarithms and you get a logarithm of a number such as 42 and you multiply it with another number such as 37 or 59 or 200, you get the logarithm of that number and you add these numbers together. Let me show you an example. 37 times 59. Now I can write 37 as 10 to the 1.5682 and multiply that by this number, which is 10 to the power 1.7709. And when I multiply these numbers together, all I have to do is add this number to that number to make this into 10 to the 3.3391.
That's like a shortcut.
Yes, instead of multiplying numbers, you're adding this to that to get this exponent. And that number, it turns out, is 2183. Instead of having to write this out longhand as 37 times 59 and work it all out in gory detail, which will require 9 times 7 and 3 times 9 and then 5 times 7 and working it out and not making a mistake, all you have to do is addition, which is much easier. And if I were to do division, I would do subtraction, which is much easier. Addition and subtraction are much easier than multiplication and division. So this is a great simplification. It makes your life much easier. The catch is that you have to know these numbers. 37 is 10 to the power of this. So where did I get that from? Where did I get 59 is this number? Well, the big secret, the thing that makes it possible, is that I have a table of these logarithms. And I look up 37. This is actually 3.7. So in order to make it 37, I have to add a 1 to it. And it's 1.5682. So that's this number. And then I look up 59. And there's 59, 59.0, I go across, it's 0.7709, but this is 5.9, so I have to add a 1. So these, I cheated, it's all in a table. I could look it up. When I was a lad at school, this is how we learned to do multiplication. I mean, we learned how to do long multiplication, but we added these numbers together to get the answer quickly. And it was the way of doing it, because there weren't pocket calculators in my youth, because I'm so old. This is all we had down mine. So when I've got this number, I have to go to a different table, which is called the table of antilogs. Now the 3 in the front of this means 1,000, so I just have to look up 0.3391. So I go down the table, there's 0.33, and then you look across the top and there's a 9, 3391. 2183, and then I look at the 1, which is this thing, and add that, and you see I get 2183, and if there was a number there I'd have to add that last one, but it's actually 0. So this is 2183, which turns out to be the right answer. Exactly. So you could get 4 significant figures by doing this, which is reasonably accurate. It's the speed, the reliability. If these tables are accurate, you can get the numbers out.
Is this just something that schoolboys and schoolgirls would use, or were log tables important for professionals?
Oh yes, log tables would be used by professionals who wanted to get accuracy, and they might not be just 4 significant figures, they might be more, depending on the accuracy of the calculations that you need to make. And they made calculations very reliable, provided the tables were reliable. But the tables, to start with, weren't very reliable, and that's really a complete story in itself, which I'd like to tell you. Well, Now you're going to ask the question, where do these numbers come from? How did I make up tables of anti-logarithms and logarithms? And this was done by a man called John Napier.